All right, so Green's theorem, what we're doing with Green's theorem is we're going to relate a line integral around a closed curve. So we're going to relate that to the double integral over the region bounded by the curve. So that's kind of an interesting idea. We have a line integral around a curve. Well, we're going to say, is that related somehow to the double integral over the region that's bounded by the curve? Now, Green's theorem is named for George Green, who was self-taught. He learned from library books. His father was a baker, and he spent his time in the library reading books about mathematics and about physics. He was one of the first people to try to come up with a mathematical theory for electromagnetism, and his work influenced a lot of the people that were working on electromagnetism at the time, including Maxwell. So Green had he came up with a lot of good ideas, and he influenced a lot of people, and our electromagnetic theory is in part based on what he found out, being a self-taught son of a baker. All right, we need to start out. We have some new terminology. So we need to define what we call a simple connected region. So the first thing we need to know is what a simple curve is. A simple curve is a curve that does not intersect itself between its endpoints. So a curve like this, between those 2 points, that would be a simple curve. A curve like this, between those 2 endpoints, going here and then coming around here, not simple. A simple closed curve intersects itself only at its endpoints. So this curve going around this way, that would be simple closed. Something like this, going around that figure 8. Not simple closed, because this one intersects itself. All right, so we're going to be interested in simple closed curves. Well, simple closed curves are related to, are we good so far? Related to a simple connected region. Now we talked about what a connected region was yesterday. Today we're going to talk about a simple connected region. A simple connected region is one whose boundary is exactly one simple closed curve. So this would be a simple connected region. And a region like this is not a simple connected region. So the second one has the boundary of the region is two simple closed curves. So we're going to be interested in simple closed curves that bound a simple connected region. And for a simple closed curve, we're going to define the orientation, the positive orientation. It's going to be clockwise, or sorry, counterclockwise around the region. And in that case, the region always remains on the left as we move in the positive direction. So our positive orientation is going to be counterclockwise, and our region as we go around the curve remains on the left. All right, so now we're ready to state Green's theorem. Are we good with a simple closed curve and a simple connected region? Okay. Green's theorem says we have a few conditions. We're going to let C be a piecewise smooth, simple closed curve. That bounds a region R in the plane. And R is going to, since C is a simple closed curve, R is going to be a simple connected region. And I'm going to say R in the plane. And I'm going to emphasize that. Green's theorem holds in the plane. So one common mistake once we learn Green's theorem is students want to apply Green's theorem all the time. We can only apply Green's theorem in the plane. And we're going to say that M of x and y and n of x and y are continuous and have continuous first partials. So I'm just going to say are nice. So we have continuous functions with continuous first partials. We don't have any strange functions. And that's in our region. They could be not nice outside a region as long as they're nice inside a region. In that case, the integral around our closed curve, so the line integral around our simple closed curve of m dx plus n dy equals the double integral over our region of dn dx minus dm dy dA. And just a reminder, this tells us we're going around a closed curve with counterclockwise orientation. All right, so this is pretty nice. The proof is a little long, and there's a lot of assumptions that we have to satisfy. So we're not gonna go through it. I think it refers to the proof in the book. But this is a very nice result. What can we conclude immediately if our field is conservative? Well, if our field's conservative around a closed path, it's 0. Both of these would evaluate to 0 because these two quantities are equal if our field is conservative. So Green's theorem around a closed path for a conservative field gives us 0. So the line integral would evaluate to 0. We already know that. Why would we want to use Green's theorem? Well, a lot of times, double integrals over a region are easier to evaluate, easier to set up and evaluate than a line integral over the boundary, depending on what the boundary is, depending on what our region is. A lot of times this is going to be easier to set up and evaluate than a line integral. Often that's the case with a closed, we have a nice simple closed curve. We're also, we'll see today, we're going to be able to relate, and I think Jacob kind of saw that a little bit. What if this quantity, if we subtract these two, turns out to be 1? That double integral over the region is the area of the region. So what we're going to do is kind of go the other way. We'll do that on Monday. And we're going to set up Green's theorem so that this quantity equals 1. And then we can use a line integral to find the area of a region, which is a kind of a cool idea. So you have some complicated region that you're trying to find the area of. You can use a line integral around the boundary of the region to find the area. So Green's theorem can help you in 2 ways. It can help you evaluate a line integral by making it a double integral. It can also help you find the area of a region by turning it into a line integral. And you can, I'll talk more about this on Monday, you can come up with a formula for the area of a polygon in the plane using Green's theorem, having to know only its vertices, the coordinates of its vertices. So if you have some 20-sided shape and you know the vertices of this polygon, you can use Green's theorem gives you a formula to find the area of that polygon just by knowing its vertices. All right, so this gives us another option for line integrals if we're evaluating a line integral around a closed path. So we've talked about the options when we have a conservative field. If we're evaluating a line integral around a closed path, we can use Green's theorem. So let's take a look at how we would apply that. So we're going to use Green's theorem. We're going to evaluate the line integral around this closed curve of y minus x dx plus 2x minus y dy. And C is the boundary of the region inside y equals the square root of 25 minus x squared. And outside y equals square root of 9 minus x squared. So let's draw this region. So we're outside y equals square root of 9 minus x squared. So we're outside this circle. There's that one. And we're inside y equals 25 minus x squared. So our region is in here. And our boundary is this curve. So if we want to evaluate this line integral directly, we have to parameterize 4 curves. Now the line segments here on the x-axis wouldn't be too bad because y would be 0. What we have to do is both of those integrals. We have to parameterize those 2 circles. The integral doesn't look terrible. Well, let's use Green's theorem. This is m, and this is n. dm dy is 1. dn dx is 2. So Green's theorem we want to evaluate the double integral over our region of 2 minus 1 dA, which equals the double integral over our region of dA. And the double integral over our region of dA is what? What does that equal? What is that thing geometrically? That's the area of the region. Area of R. Well, we can do that without even integrating, can't we? Isn't it the area, the double integral over a region of dA, is 1/2 pi times 5 squared minus pi times 3 squared? 8 pi. In this case, Green's theorem saves us a lot of work. If we, if this didn't turn out to be, what would we do to evaluate that double integral? How would we set it up? Polar coordinates. Theta equals 0 to pi, r equals 3 to 5. It wouldn't be bad.
So hang on. In the conversation earlier, this is defined by 2 paths. Is that okay for the region to be defined like that and not the function? Because you're saying like about the simple connected region.
Yeah, it's bounded by one piecewise smooth.
Okay, so it doesn't have to be only one function.
No.
It just has to, all the functions have to be connected into one big piece. Okay.
Right, yeah, so we said it could be a piecewise smooth simple closed curve.
Okay.
For Green's theorem. As long as there's the boundary is just one piecewise smooth closed curve.
So there's only one edge.
There's one edge.
Okay.
Yes.
So it's okay if that edge is defined by many functions.
Yeah.
Okay.
Yeah. It could be defined by as many as we want.
If you add like a washer though, could you do the outside one and subtract the inside one? All of it?
I don't think so.
And how would you go about it? You just can't use this. You need
Right.
to set up the line.
You'd have to set up the line. All right, let's look at another one. So we're going to use Green's again. Double integral over our closed curve of y squared dx plus xy dy. And our curve is the boundary of the region. Between y equals 0, y equals the square root of x, and x equals 9. So let's draw a picture. There's y equals square root of x, y equals 0 is here, and here's x equals 9. So our region is in here. This is our boundary. We have a piecewise smooth, simple closed curve. The bound's a simple connected region. So the other way that this question could be asked is find the work done moving this, or by this field, moving a particle around that closed path. Or we're going to use Green's. So the partial of m with respect to y is 2y. Partial of n with respect to x is y. So by Green's, we evaluate the double integral over our region of minus y dn dx minus dn dy dA. Well, this is easy, right? How are we going to set this one up? Y is going to go from 0 to, if we set our rectangles vertically, y would go from 0 to square root of x. X is going to go from 0 to 9. And we just get minus y dy dx. Easy integral to evaluate. We get minus 81 fourths. I think this and this double integral definitely easier than parameterizing 3 curves and doing our 3 line integrals. Not that those line integrals would be difficult, but that would be more work. And this double integral is easy to set up. All right, questions? All right, let's look at one more example. This is the kind of the big example of when you should think, can I use Green's theorem? Or when can I make my life easier? We're going to make this integral e to the x cosine 2y dx minus 2e to the x sine 2y dy. And our path is x squared plus y squared equals 9. All right. So if you were just given this line integral, evaluate this line integral. If you started parameterizing your curve and representing your function in terms of parameterized curve, we'd have e to the cosine theta, cosine of 2 times the cosine of theta. So we'd have the cosine of theta, e to the sine theta, sine of 2 cosine theta. That would be really messy. That would be a really terrible integral. But we have a closed curve. And we have a line integral. So we should think, is it conservative? If it's a closed curve, should I use Green's theorem? If it's a closed curve, I always think, well, let's try to use Green's theorem. Well, test if it's conservative first, but if it's not conservative, use Green's theorem. Well, let's see this, if this is conservative. dm dy. What do we get? Take the derivative of this, so we get minus 2 e to the x sine 2y. dn dx is minus 2 e to the x sine 2y. This is conservative. The integral evaluates to 0. We're done. We took a couple derivatives and we're done.
And even if it's really conservative, you still need those two pieces for Green's theorem.
Right.
So you should always just do this operation, and if they're the same, it's conservative, and if they're not the same, it's not doing Green's theorem.
Right, exactly. So we need these two things for Green's theorem. So this is the first step in doing Green's theorem, is taking these partial derivatives. So if you have a closed curve in the plane, that should be your first step. Make sure that if you're applying Green's theorem, that you have a simple closed curve in the plane. Once we start doing Green's theorem, students want to apply Green's theorem to every line integral that we do, because it's really nice. But Green's theorem only works for a simple closed curve in the plane. Now what we're going to do as we move towards the end of the chapter is we will we'll kind of come up with some different versions of Green's theorem, and we'll come up with a three-dimensional version of Green's theorem, and that is Stokes' theorem. And that's when we'll finally talk about what our physical interpretation of the curl, when we talk about Stokes' theorem. All right, questions? Okay.
So the objective of this entire thing is to do as few line integrals as possible.
That's with path independence and Green's theorem, yes. Try not to have to do line integrals.
So we all have to do the line integrals, do a quiz on the line integrals, and then we got to learn all the tricks to not have to do that.
Right. Well, sometimes you do have to do them.